Hi, everyone. Welcome to this webinar presentation on the process industry called Develop Sound Universal Skills for the Process Industry. If everybody's ready, we're going to look at today's agenda. But maybe, Gonzalo, you want to say a few things about GoToWebinar. Not everybody has used it in the past, so maybe you can say something on that.
Yes, good afternoon, Francois Xavier, and welcome everybody to this webinar about process control. So today I'm going to be with Francois Xavier. I'm going to be handling the questions and the chat. And if you have more advanced questions that neither Francois Xavier or me we cannot answer, then we have also as a very big support, Mr. Stefan Cass. That's the product manager for this product line. Within the GoToWebinar screen that you see, you can click over either Francois Xavier's picture or me or my picture, and then you're going to have it in full screen. So you see, you have in the GoToWebinar, you have the question box in one of those gray bars, the chat box in also those gray bars, and the handouts. If you're interested in the handouts, just click on them and download them before the webinar is finished. Also, this webinar is going to be registered, and 24 hours after that webinar has finished, you will receive the video of this webinar. Welcome again, and let's get started.
Thank you, Gonzalo. So back to the agenda for today, we're going to describe first who we are at Festo Didactic. We're going to look at the process of devising new learning solutions. We're going to introduce the process automation, what it is, and then we're going to do a demo exercise before we go to the questions that you may have. As you may know, Festo was founded in southern Germany in 1925, specializing in woodworking machines such as the world's first portable chainsaw in 1927. In 1955, we switched to pneumatic technology, which was very, very promising at the time. And in 1965, it was the foundation of our didactic branch. In 2004, more recently, the US-Canadian Lab Vault and Festo Didactic merged, and we became one company. And now in 2020, our portfolio looks like this. We do have some fluid power learning solutions. We do have some factory automation, but we have, of course, process automation, which is the subject of today. And if you look a little down on the slide, you will see that we have also a lot of products in electrical engineering, communication, industrial trades, HVAC, and so on. This is the building where we're located in Quebec City. Stefan Cass is in the middle. You see a picture of him. He's the product manager. Gonzalo is the one guy on the left. I'm the one in the middle. François Xavier is my name. And Christian Remillard on the right. He's preparing the next webinar, apparently.
So right now we have Stefan sharing his webcam. So good afternoon, Stefan. Welcome.
Good afternoon. I'm really happy to be with you, gentlemen. I'm happy that you will see the industrial didactic solution that we have created to bring really the student close to what they will work with in the field. So I'm from the industry. I've been working with Festo Didactic for more than 20 years. And when I was working for the other companies before, I was working for pulp and paper and chemical companies. And this is what I wanted to bring with me, the experience that I've got. I wanted to transfer that to a didactic product. And this is what you will discover today with our industrial learning solution. Thank you.
Thanks, Stefan. And let's go back with Francois Xavier.
Thanks to both of you. Our learning systems are always designed as follows. This is the standard process that we now have. First, we gather industry specialists, teachers, experts in-house, and they get together and they devise a list of learning objectives. After they have these objectives, they divide them into exercises, and it's only then that they can think of the equipment that will be required to go with these lab exercises. Finally, we end up with a prototype, and the technical writers, they will write the books according to what we did before. I was a technical writer myself. I wrote some of the book of the series that we're going to discover today, and it was a pleasure working with Stefan more closely. Now we still work together, but we have different positions. Concerning this series of books on industrial process control, it's really extensive, the number of manuals that we have. We count 40 students' manuals, 24 instructor manuals, and they are arranged as you can see on the screen. We always have one user guide that we call the familiarization book. We ask that the students and the teachers, they read them before they start the measurement exercises, followed by the process control exercises or the advanced process control exercises. As you will see, we have many options with the system that we have here. That's why we have optional manuals to go with these different options. In any particular exercise, it will look a bit like what you see at the bottom of the slide. The students, they will build their loop according to the PNID, and then they will connect the electrical wire, they will configure the transmitters and the controllers, they will tune the loop, and they can do some troubleshooting at the end of the exercise too, because there are some faults hidden in the system. This is an extract from one of the familiarization book. It's to show you the level of details that you can expect from such a book. This one is showing the drive and one of the transmitters, and you see that everything is well laid out. It's much it's much easier to read like this than using the original manufacturer's books. From the beginning of this project, the team wanted a realistic system that was easy to work with in a learning environment. Sometimes you have one or the other, but we wanted both. We didn't want just a simulation or something that's, well, we didn't want to go to a plant and work with real equipment in operation in a distillery per se, but we wanted the industrial feeling anyway. So that's why we came up with this solution, which is realistic and didactic, has a high didactic value. Now let's explain the concepts of process automation a little bit, because you may not be all that familiar with process automation. There are three main technical areas in which workers can specialize: process control, instrumentation, and process technologies such as the use of water. We also, some industries that rely heavily on process automations are listed below. This is just a couple of examples. Beer companies are one of such industries, and power generation companies too, of course. That being said, why should we be concerned about process automation in our learning centers? When everything goes well, you have a rainbow and it's all good, but I don't know if you remember some 10 years ago in the Gulf of Mexico, there was the Deepwater Horizon explosion, and that's something that may happen if you have a lack of training, of experience, of maintenance. this can lead to a catastrophe. Sometimes we're asked, what's the difference between process automation and factory automation? In general, we can say that with process automation, we're more concerned about analog signals compared to digital signals. The response time is slower in general again. And in the case of process automation, we use pressure, flow, level, temperature transmitters. We use pumps and control valves. Whereas with factory automation, we're more concerned about digital sensors on the drives, motor drives, the magnetic valves. And it's more of a sequential control as opposed to continuous control. Now we're gonna start a video that tells you a little bit why a student should want to learn about the industrial instrumentation technology. It will be just all right. I hope you now know a bit more about how industrial process control is being taught. We've been working with the PTC for a number of years now. Gonzalo, you seem to be busy. Do you have any questions that may need some attention from us?
Just only have standard questions about sound and audio, and everything is
Okay.
fine for the moment.
Okay, so we'll keep going.
Okay, if you have problems with the audio or the video, sign out of the webinar and please come back. Normally this resets the audio and the video and they start working. We have around 5 to 10% of the computers of the attendees that normally they don't work. Is something about Windows. Sorry about it. We can call Bill Gates to solve this problem. Keep on going, François Xavier.
All right, thank you, Gonzalo. If we want to summarize what we need for a process control loop to work, there are 3 key elements. First one is sensors and transmitters. You have an example here with the RTD. We also need a controller to take a decision. It can be a dedicated PID controller like the Foxborough, a PLC, or a computer-based controller. Finally, we need an actuator. In our case, we use valves. We use also heating and cooling units, and the variable frequency drive with the pumps to have a different flow of water. Now, if we want to modelize the control loop, there are 3 main parameters to consider: the set point, SP, the process variable, PV, and the controlled variable, CV. If we take a level loop as an example, if we measure the PV, which is the first step, the PV can be the level in the tank. Then we need to compare that value, that PV, to a set point and calculate the error. In that case, when we have a level process, we want, say, 50% of the total height, but we're at 40%, so there's a gap. That gap is our error. And finally, we need to take action. The controller that we have will send a control signal to the control valve to open up a little bit more so we can reach that desired level of 50%. Another way to present these concepts is with the typical block diagram that you see on the left. The set point is represented on the left of that diagram. We subtract the process variable value that is measured from the set point, and that's the error that we were talking about. This error will be used by the controller to produce the output CV. In this case, it's a valve that will be opening, and the opening of the valve has an effect on the process, and in turn, the process variable will change with time, and hopefully we will reach our set point. There's another parameter that's indicated on the block diagram, and it's the disturbance. It can be a valve that is open, and that has an effect on the different variables, because more water will exit the tank if that happens. We have another video here showing you the daily job of an instrumentation technician. If you just give me a little second, we will start that video. It was shot in Cold Lake, Alberta, at the Imperial Oil facility. I hope this video gives you an idea of what the job can look like in the field. And I hope also that you recognize some of the transmitters that were used by our technician during the video. I'm going to look at Gonzalo to see if everything is working well in the chat section.
Yep, right now in the chat we have several questions, but those are general questions. So right now everything nice and sweet. So you can keep on going, FX. Everything good.
Okay, we're now getting closer to the demonstration part. Already, we have a better knowledge of what process automation is and what the job looks like. What we'll be using for our demonstration is the system that you see here in the middle. What we want to say is that it's made out of two workstations. On the left, you have the equivalent of the process operation floor, what happens in the plant, and on the right, you have the equivalent of the control room, where you have the technicians and engineers maybe devising the next PLC program for one of the processes. Let's take a deeper look now at what we have for components. We will be using some of these industrial components shortly. The valve in green from Fisher, we will be using something similar to that. We will also be using a variable frequency drive from Rockwell, as well as Compact Logic's PLC. But you see that there are other options for control if we wanted. We just wanted to keep it simple for today. In terms of transmitters, we will be using the one on the top left corner. It's a versatile differential pressure transmitter from Andres and Hausa. What we do during the exercise, we have different steps that we have to follow. It's all laid out in the books. Step one is usually setting up the hose connections according to the diagram that you see on the left. And on the right, you see what it should actually look like when the hoses are connected. Our goal is that students can read what's on the diagram and apply it to the system. Our second step will be the wiring, the electrical wiring and the configuration of the differential pressure transmitter. The electrical connections are shown on the left. You have a diagram first, and then you have more specifically the connections for the differential pressure transmitter and for the valve. And I will ask Gonzalo to turn on his webcam so we can maybe do a little tour of the station together.
Please double click over the picture of my webcam so you can have it in full screen.
Ready, set. Okay, let me start with the tank that's located here at the bottom. It contains up to 16 gallons of water. We put some blue coloring in there for fun and because it looks nicer. When you have a temperature application, you can have a red water and blue water, then it makes more sense. When you only have room temperature water, then it doesn't matter really. We have a series of pumps at the bottom. We will be using just one of the pumps, and the water coming out of that pump will go through this rotameter here. Notice that we have the first hand valve that we can play with if we want to. It's fully open now, but I can close it entirely. If we follow the hose, we get to the control valve I was mentioning. This one doesn't have a positioner. The 4 to 20 milliamp is acting on the valve, and it will open and close depending on the signal it receives. And then more or less water will flow to the bottom of our column. Right now it's 1/3 full, but if I open here, you'll have less water. So we can measure visually with the eyes what's the height, but with the differential pressure transmitter that's here, we can also know what is the level in the column at the same time, so we can compare the two values. If we read 11 inches here, is it what I get on my differential pressure transmitter? That's one of the exercises that we could do. We can also open here and do like our technician Lafont did in the video, and do the setup and the commissioning with the buttons. There are other options. We could also use hard technology to hard communication to set the parameters, but we start usually by doing it by hand using the small buttons that are here. Finally, if I want to close the loop, we have these two hoses. The first one I showed you already, and we have another hose that passes through a solenoid valve. If the valve is actuated, if we have 24 volts here, then this is open and water can flow back to my hand valve number 5 in the tank in this case, and it all goes back to the tank I was showing you at the beginning. Now for wiring, that was for the hose connections. For wiring, we see that we have electrical wires going to the differential pressure transmitter, to the control valve, and they go all the way to my PLC here. We will be using input 0 and output 0. And what we also need is this cable just to assure that, well, it's a safety feature. And I think, and the solenoid valve will be connected through here. So this is for the wiring. We will go back to the PowerPoint presentation. Before we use the interface to start the system and to tune it and to have fun, really. All right, now back to my slides here. I hope that you can see. These were steps 1 and 2. Step 3, we will start the drive. We will adjust the parameters. We will check the stability of our control loop by changing the set point, and we may or may not create a disturbance by changing the pump speed or choking the manual valve, maybe HV2, the hand valve number 2. So I think we should do that now if we can. We'll stop the presentation and we will be back after a few minutes. Gonzalo, if you want to switch on the camera. Okay, I hope that you can see. Your camera's on. Good. Let's take a closer look at our interface here. The drive, the PLC, and the screen, they're all connected together with Ethernet IP. We're currently in manual mode, and the pump is not active. I will start it at 30 Hertz and see if anything is leaking. Not that I'm worried, but it's always a good practice to start the drive at a low value and check that all our connections are fine. Now that water is rising, I will go to the configuration of my loop. We will make sure that our inputs and outputs, they're connected the same way that they're configured. If I go to my loop 0, I see here that analog input 0 will be my PV, and analog output 0 will be my CV. We have some random values for proportional, integral, and derivative. We may as well start with just an integral proportional term. We will make it really low and see what happens. Please note that we have one type of algorithm that's an independent gains form. The beauty of it is that the proportional, the integral, and the derivative, they are separate. So you can play with each of them independently and see what happens. What we'll do, we'll just have the first term here, KPE, active once we go to auto mode. Let me close this window now, put it to auto mode. And I will set my set point to somewhere close to 50, 55. Let's see what happens. When you only have a proportional term, you will not be able to reach the set point exactly. There will always be an error, a residual error. But if you increase your KP, you'll see that error will be a bit less. So I will exaggerate. We had 1, let's go to 8, and let's see if it will cause any instability. We'll change the set point, see what happens. The set point is at 57. Now, my control variable is all the way up, meaning that the valve is entirely closed at this time. Of course, this has the effect of bringing the process value down. But now, every time that we go over or under our set point, the proportional term increases or decreases a lot, and that causes stability. We go way under, way above, and I don't know what you think, Gonzalo, about it, but maybe we should change the parameters.
Yes, right now we're seeing that we have an oscillation. Let's give it one more shot. Yeah, we see that it's not even damping oscillation. Maybe it's a constant of oscillation. If it is a constant oscillation, it will be a very good thing if we were going to make a Ziegler and Nichols or ultimate cycle. But now we're making a trial and error. So I would think you can go maybe halfway back between 8 and 1, so we can have something more smooth and we can make another change point.
Okay, how
Change
about
in the set point.
4?
Francois, can we get a specific set point, for example, let's say 50%? Is it possible?
It is possible.
Oh, thank you.
To me, it seems a bit more reasonable. the slope is not as sharp as it was. We could spend hours like this trying to fine tune the system, but what we'll do, because our time is short, it's not too bad actually. We're going to, and this is the trial and error method, so we could of course calculate, use the Ziegler-Nichols method, but not today. We are going to put a little value here, a little bit of integral term, and see what will happen. Let's go to 60 now. Huh.
Oh, that was really good.
Yeah. Okay. I don't know if you want to go any further with the demonstration, Gonzalo. What's
Um,
needed to?
yeah, I think you can make a small tour about what kind of equations we have, and
Okay.
just a quick tour of the controls and how many loops, how many simultaneous loops we can control with the system.
Yeah. Good point. So let me switch to manual mode from here. I will stop the pump, so I don't have to speak that loud. And not that it's that bad. I think that our mic is doing a good job in that regard. You asked me how many loops we can have. We can have up to 8 different loops at the same time. This goes with the PLC that we have that has 8 inputs and 8 outputs. In terms of the equations that we can use two forms of equation. We use the independent form, but we can also use the dependent one. And for each of them, we can have the position algorithm, which is more, which is calculated differently, and it depends on the past value. With Rockwell Automation, there are different equation. You have advanced calculation, but this is inside the programming of the PLC. The difference. It will still be a PID control, but the way it's calculated will be different. And if you want to play a trick on Gonzalo, you hit the PID disabled, and next time you will use PID loop 0, it will not be working. We can have two drives working simultaneously. We just have one installed, drive 1. We can look at the different PID loops. We can access all the inputs and outputs, whether digital or analog. And we support field bus communication, hard communication. There's a way to have fun for a couple of days or weeks or even months playing with this interface. So that sums it up. Gonzalo, unless you have something else to mention.
Yeah, I think we have done a quick tour about the system. So, as Francois Xavier was mentioning, we have the system, and this system can be loaded with several different kinds of equipment. We can have Siemens PLCs and touch screens, Allen Bradley PLCs, and of course touch screens. Also, in the system, we can have different configurations. For example, here we see the metering pumps that we can make pH, we can make temperature process controls. So there's a very large variety of elements we can load in the system depending on what are your needs in education. So we can fit and load the system exactly to fit your program as much as possible with different kinds of sensors, valves. So our goal is to be able to match with our system what is most useful and most normal to see in the industries around your school.
Yeah, some say it's extremely modular.
It is extremely modular.
All right. We're getting to the end of the presentation. Now, I hope, okay. Now that the demonstration is made, if we want to summarize our didactic solution, we can say that it is supported by an extensive curriculum based on realistic industrial situations and fostering troubleshooting skills. The system is of industrial grade, modular, and expandable. Finally, it's safe and supported by a strong team for years to come. And now is the time for some questions. And since we have Stefan on the line, he can show his camera, and together we can answer some of your questions. Ah, je t'entends pas ta caméra.
Hello, Stefan. So here we have, I was gathering some questions for you. One of the first questions is, what is the advantage of using a DCS compared to a PLC? Oh, Stefan, I think your microphone is muted.
Sorry
Can't
for
see
that.
you well, though.
Yeah,
Yes.
now we can hear you.
So in the past, if we look back 20 years ago, the PLCs were not programmed the same ways as they are now with DCSs. The big difference with DCSs is the way to program the controllers. So Rockwell now they have developed libraries to be able to program the PLCs similar the way that you program other PLCs like Delta V PLC or the PCS7 from Siemens, and they use the similar approach, similar block approach. So now PLCs are very close to the DCS's approach that we used to have in the past.
Perfect. And we have here another question.
And we also have a DCS solution that we can provide. So today we presented the modular approach with the 3531, focusing on instrumentation and the different process variable that you want to control. But we also have an advanced system, a demonstrator, demonstrating a Plan PX DCS, and with all the different communication protocol integrated like the student would find in a plant. And these the Plan PX demonstrator is a demonstrator that integrates some layer of protection, networking, because I saw that there was a question about a layer of protection. If it's covered with our system, it's not directly covered in the curriculum, but with the Plan PX DCS demonstrator, it is possible to provide cybersecurity training with the switch. And we had in the past some customer who use that system to train their student about cybersecurity, like the US Army in the US. So you
Perfect.
Yeah. Is there a question, Gonzalo?
Yeah, I'm searching. There were a lot of questions, but most technical related. Yes. Yeah, well, I have a question here that is, if you're going to have the video available. Yes, the link for the video is going to be available 24 hours after we end the live presentation. You will receive an email, and as such that you are registered already in this video, in this webinar, you will have free access to the video.
Good. And well, Stefan, I don't know if you have any question that you wish you had today.
Yeah, kind of question that I usually get is, yeah, but what I want to cover with my student is not exactly what the systems looks like it provides, but the best way is to meet with us, meet with people from Festo Didactic, and the system is so modular that you can tailor exactly the need that you need to fit. So you can start small, select having a basic system, train your student with pressure flow level. Then the year after, then you can expand it with other additional component. And also, let's say that in your area, you have, let's say, petrochemical companies. So the instrumentation that you would need to train your student on would not be the same as it would be more, let's say, a water treatment plant. So according to the needs that you have in your area, we can select with you exactly what the student will need to be trained on. So this is something that is very important to have in mind. And you can select different technology regarding the controller. You can go with Siemens, you can go with Allen Bradley, or use Honeywell PID controller, or because it is a double-sided system, you can have two teams working at the same time, one at the front, one at the back, and you can have the Siemens technology on one side and Rockwell technology on the other side.
So many options, it's crazy.
Yes, and there's the last question that just arrived. It said, what APC is covered? I imagine is advanced process control.
Yeah, advanced process control. We have a specific curriculum for advanced process control, covering second order process, split range, ratio, feed forward process. And what we cover with a basic process control is PID and cascade process control. And we also have, you know, we can simulate a boiler with the system. So you can do 1 element, 2 element, and 3 element process control like you would do in a real boiler.
Yes, and the only thing is that well, it's available for everywhere in the world except the European Union for now. Is that correct? If anyone is asking.
Yeah, it is correct. It's not CE mark yet.
Okay, thanks, Stefan. And there's the last question here that just arrived. Advanced regulatory control. Do we cover that in our books?
Pardon me, could you repeat the question, please?
Do we cover in our books the advanced regulatory control?
Yeah. We have a specific workbook for a student covering the advanced process control approach strategies with exercises.
Perfect. Thanks, Stefan. Well, I wanted to, yep. So yeah, I just want to remind you that Professor Xavier told you during the presentation that our system comes around with 40 books depending on the configuration, and always we have student book and teacher book. So the way you're going to teach the classes is pretty well done in our books. So at least the first session that you're going to use our system, you may stick to our manuals and you're going to see that we grab the student by the hand and we train them very well, and we start from very basic to a very high level. And then when you get used to the system, you can start making your own labs. So it's a turnkey solution for most of the schools.
And what people do sometimes is they order, well, we can have samples of the books so you can look for yourself, do some reading, and see if it matches what your requirements at your school, at your program. So that's something we can do. You just have to write to the services team, and we will answer to you gladly. That being said, I think that sums it up. Thank you. Thanks to all of you for watching. It was a pleasure from our side. We hope to see you next time. All right. Have a good one. Take care.
Thanks so much. Good afternoon.